So in this lesson, we're really going to focus on graphs of quadratic functions in the quadratic functions chapter. All right, so our big learning objectives. In previous courses, you've investigated linear and exponential functions like straight lines or exponential curves like growth and decay. And in this chapter, we're going to study quadratic functions. It's another family of functions. We're going to learn about their graphs and fully describe their features. And the graph of a quadratic function has the shape of a parabola. So we probably have heard this word before, but maybe it feels like a long time ago. So it's a parabola, the shape of a quadratic function. All right. And here is our essential question. What are the shape, which we just talked about, and key features of graphs of quadratic functions? So I'd like you just to take about, 20 seconds and jot down anything you can think of involving the shape of a quadratic function or its key features. And if all you've got is that I just told you it was a parabola, then go ahead and put that, okay? All right, so this is a list of the key features of a parabola, or of a graph, excuse me, of any graph, but in particular, we're looking at quadratic functions. So in a quadratic function graph, there are things that we're always looking for. So first of all, we always want to be able to identify the shape of a graph. Sometimes it's a line, sometimes it's a parabola, sometimes it's a wave, like there's all kinds of shapes. So in general, for what we're doing right now, we're going to be focusing on parabolas for the shape of the graph. And each parabola that we will deal with will either open up or down. So you can see over here, we have an upward opening parabola where the arrows are pointing up, and a downward opening parabola where the arrows are pointing down. And the arrows imply that it's going to continue going forever. But a parabola looks like sort of a U if it's opening upward, and sort of like an N or a mountain, an upside down U, it's going downward. Each parabola, we do have also, there's such thing as a sideways parabola like this that opens horizontally, but we're not going to consider those today or in this chapter. Those are not functions, whereas these are functions. So each parabola has a maximum or a minimum point. And by that, I mean like a high point for a maximum or a lowest point for a minimum. And so in our open upward parabola, do you see how if you're on the curve and you're just sort of tracing the curve, you trace it, trace it, trace it, trace it, trace it, you hit a lowest point and then you keep going and it's back up. So this lowest point would be a min. That's a minimum. That's also very messy. Okay, so we have a minimum on an opening upward one because it's a low point. It's kind of like a valley. So you'd go down the hill, you'd hit the bottom of the valley, and then you'd have to work your way back up. Whereas the other one, you would climb the mountain. You're climbing up and up and up, and you hit the top, and then you can come back down. So there's a high point here, which is a max. So we have a minimum or a maximum depending on the graph. And each minimum or maximum is located at this very, very important special point called the vertex. The vertex of a parabola is always that key point, that maximum or minimum point, the highest or lowest point. It also happens to be the exact sort of pivot point where we change from going uphill to downhill or downhill to uphill. It's that point where we have sort of symmetrical sides on either side. And that brings us to our next term, which is the line of symmetry. So each parabola that we deal with is perfectly symmetrical. And that means that there will be a vertical line I can draw right through the vertex that it will be identical in shape reflection-wise, excuse me, I'm sorry, my eye, reflection-wise on either side of that line. So there's one here too. There will always be this vertical line that goes through the vertex called the line of symmetry, that it's like identical on either side. It could fold perfectly over on itself. And then when we have a parabola graphed, we're looking for all these key features. We're looking for x-intercepts, where it crosses the x-axis. We're looking for y-intercepts, where it crosses the y-axis. We're looking for the domain, what x values we can use, or inputs we can use in the equation, and the range, what y values. And we'll get into this more deeply when we do an example. We're looking for where it's increasing and where it's decreasing. And what I mean by that is a graph is increasing when it has like an upward growth, when it has, in like for a line, it has like a positive slope. So an increasing line is when it's going upward. A decreasing part is when it's going downward. So when we're talking about a line, that's easy to make a distinction. We just go, oh, this has a positive slope, it's increasing forever. Or a line would have a negative slope, it's decreasing forever. But in a parabola, we actually have both. We have both increasing and decreasing. So let me change my color for decreasing here. So I think that it will make like a nice contrast. So let's do decreasing in this color instead. So I want you to see how in this graph, we read from left to right, always, just like with a sentence. If I start up on the top left of this graph and I just follow it, do you see how it's going downhill like this? That's a decreasing. So that tells me I'm decreasing there. When it's going uphill, like over here from left to right, this tells me it's increasing. Positive sort of growth on the right, negative growth on the left, right? It's like getting lower or it's getting higher. Okay, and we'll get into that more too with an example. And then, is it a function? And today, a function means for every input, there's only one output that goes with it. So it can't loop back over itself. And all parabolas that open upward or downward are functions. They're going to keep on going in a safe way where every input gets its own one output and it doesn't loop back over. Okay. All right. So this is just sort of like a overview slide. But now we're actually going to apply this and get all of the details of an actual graph. So here we have a graph given to us, and we have an equation to go with it, which is always really important. We have an equation, see how it has x values and y values. So we have now our function notation, our function like format. So we can input y's and output x's. There's a table here that we're going to want to fill in with 5 key points, and we're going to wait on doing that together so that we do it in a strategic way. And then this is our list of details. So we're going to go ahead and start our list. So our shape is always going to be a parabola when we're dealing with a quadratic. And something to look for to determine whether it's a parabola is this term right here. We have an equation, y equals a bunch of terms involving x, and the highest exponent and variable we see is x to the second power. This tells us it's a parabola, that it's a quadratic. And then we want to decide if it opens up or down. So one way to do this is to look at your graph and make sure that you have arrows on the ends of your curve. You see this? So if we put in arrows at the ends, that tells us that we have a graph that's opening up because the arrows are pointing up. And now, because our graph is pointing upward, it's going to continue up forever, which means there is no highest point on this graph. It goes up and 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 up forever, which means there's a lowest point. Do you see it's like the valley? So this is our minimum down here. So this graph has a minimum. and the minimum will be located at the vertex. So let's identify the vertex. So you see here, there's this middle point of the curve, right down at the bottom, the lowest point. And we have an x-axis here and a y-axis here. If we go over 1 and down 9, we get to our vertex. So we have a vertex at the point 1, -9. So I labeled it on the graph just so you can see that connection, but I'm going to put it in my list too. Oops, 1, -9. Thank you very much. Okay, so here's our vertex. Don't forget your parentheses. It's really important that when you're writing a coordinate pair like this, that you have parentheses around it. Okay. So far, is there anything that I can clarify for you or you need help with or an explanation again? Go ahead and put your questions in the chat. And I recommend you use the typing tool because most of what we're doing today is typing. And if you normally do things on a separate sheet of paper, that's going to be really tough with these graphs and all of this detail that you have to write down. It's a lot of extra writing. So I do want to see everyone responding on the slide. So I see a handful of people not doing that. I'm looking for you for your participation, everyone. Okay. Okay, so we're recording again. Here we go. So we're going to go ahead now and we're going to write in the line of symmetry. Okay, so I'm going to draw it first. So the line of symmetry goes through the vertex. It always goes through the vertex, and it's a vertical line right through the vertex. And then when we want to write the equation of the line of symmetry, this vertical line passes through the x-axis at 1. So that tells me that it has an equation of x equals 1. This is not always the easiest for people to remember. So another way you can think about this, is to connect it with the vertex information. So we have x equals 1 for our line of symmetry. We have our vertex at 1, -9. This is not a coincidence. The axis of symmetry always goes through the vertex, which means the 1 from the vertex and the axis of symmetry 1 will be the same number always. So if you can find the vertex, you can write the line of symmetry. Okay, those will always be the same. Okay, so we've got our line of symmetry. Now, let's get our intercept. So you can see how it crosses the x-axis here at 2 points. And each of those points is an x-intercept where it crosses the x-axis. So here we have one at -2, 0, right here. And there's our first x-intercept. And here we have another one at +4, 0. Okay, so I'm going to go ahead and put those in my list. And the symmetrical nature of the parabola often means that we'll have 2 x-intercepts. Sometimes it has 2, but it doesn't always. Sometimes the parabola comes along in and just hits the x-axis 1 time and there'll only be 1. Or sometimes it doesn't reach the x-axis at all. It turns around before it even reaches it, and then we have none at all. But in this case, we have 2. All right, now y-intercept. It looks like we cross the y-axis down here, and that's at 0, -8. Okay. So I'm going very slowly through this example, but we will go much faster through the next one. All right, so notice how for the x-intercepts, the y coordinate, the y in the coordinates are 0. And for the y-intercept, the x is 0. So that's going to be something that will always be true. All right, now before we go to the rest of the descriptors, I think it's time to fill in our table. So when you fill in a table for a parabola, you can fill it in whatever order you want to, but ideally you actually do it very carefully and strategically so that the vertex is the middle point. And because when the vertex is the middle point, what you start to see is symmetry in the numbers on either side. It becomes like a nicer, clearer sort of visual, like numeric representation of the visual. So the vertex was 1, -9. We figured that out. So I'm going to put that as my middle point. I'm going to put that as my middle point in my table. And then let's get some symmetry going here. So I'm down here at my middle point, 1, -9. I have my y-intercept. Oh my goodness. Okay. And my y-intercept is 0, -8. And because it's symmetrical, even though there's not a point highlighted there, there's another point over here that's 1 unit away from the green line of symmetry on the other side, which will be like the symmetrical point with 0, -8. And that one is at 2, -8. So I'm going to use that point as well. So now I'm going to go back to my table and I'm going to put 0, -8 on one side of my vertex. And I'm going to put 2, -8 on the other side of my vertex. Do you see how we have symmetry there? How the y's on either side of the -9 are both -8 on either side. We have this like perfect symmetry in the y's. And then finally, let's use our y or our x-intercepts. So I'm going to go ahead and put those. So we have -2, 0 on that end. And then we have +4, 0 on this end. So you can see now there's a pattern. There's a pattern in our table. You can see how we have the vertex right in the middle as like sort of a pivot point. And then we have -8 and -8 on either side, and then 0 and 0 on either side. Like it's symmetrical on either side. The other thing to note is that even though the x values are not symmetrical per se, they're spread out evenly from the vertex in their own way. They're equal distance from the vertex on a number line. So like the red numbers are 1 unit below 1 and 1 unit above 1, so 0 and 2. Or 3 units below 1 at -2 and 3 units above 1 at 4. So they're balanced out in the x's as well in their own way. Okay. All right, let's do some domain and range. So the domain is all of the input values for a particular graph. So that means all of the x values that are being used here. And that's when we think about the x-axis, think about all the numbers we're using. When we plug in a 1, we get -9. When we plug in a 2, we get -8. When we plug in a 3, we get something down here. When we plug in a 4, we get a 0. When we plug in a 5, it's going to be way up there somewhere. I can plug in any positive number I want to, and this would just continue, and there would be some place for it out there somewhere. Same with negatives. Plug in a, or 0, plug in a 0, get a -8, plug in a -1, get a -5, I think, plug in a -2, get a 0. And I keep on plugging in negatives, and I'm still going to get points on this graph. When I look at the equation, think about what I can put for x. I could put anything I want for x. I could even put decimals for x. I could put fractions, decimals, square roots, irrational numbers, any kind of positive, any kind of negative. I can input them and there will be no like problem with that. There's no time where it would force me to divide by 0, which isn't allowed, or where I would have to take a square root of a negative, which isn't allowed. I have no boundaries. For a parabola that opens up or down, the x values, the inputs, are unlimited. which means they will always be the same answer. The domain for all parabolas opening up or down is all real numbers. This will always be true for every parabola we work with that opens up or down. The domain is all real numbers, no matter what. If it's a continuous curve with arrows that opens up or down, it will always be all real numbers. There's no boundaries on this, but the range is different. The y values that are being used are different. No matter what I plug in for x, something happens to y that's unique to y in this situation. If I plug in a negative number for x, I'm going to get out, like, if I plug in -2, I'm going to get out a 0. If I plug in +4, I'm going to get out a 0. There's balance here. In my vertical direction, I have these y's up and down. I'm using all of these, and then the graph stops at 1, -9 and goes back up. So we go down, 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 stop, and go back up. Look at the table. I'm getting smaller and smaller numbers, 0, then -8, then -9, but then they go back up again, -8 to 0, and so on. -9 is our lowest number we can ever have in the y direction. That's our cutoff. If I put like a cutoff line along the bottom, you could see we'll never go below this yellow line. We're never going to go below it. It just looped down and went right back up. So what that tells me is that my range, my range is going to be y values that are always bigger than -9 in this graph. But they can be equal to. So I don't have that symbol. So what I'm going to do is go in and I'm going to write greater than or equal to symbol. Greater than or equal to -9, because I have to keep it at -9 and up. Okay, Michael, that's fine. All right. Okay, last part. And this is like a weird one for some people. So, I'm going to try to do my best here. All right. So when we talk about decreasing and increasing, this means, is the graph going down? Is it going downhill? Does it look like a negative slope or does it look like a positive slope? So on the left-hand side of this graph, we always read from left to right. I just start following the curve, and this is all downhill arrows. Do you see that? Until I reach the vertex. And then I start going back up. Let me change my color. Up. These are up. Okay. So when I read the graph, when I trace the graph with my pencil, I'm going down and then back up. Down with the purple arrows, back up with the blue arrows. So, and the changing place is at the vertical line of symmetry. So what this tells me basically is that on this side of the line of symmetry, the whole thing is downhill. On this side of the line of symmetry, the whole thing is uphill. I know that's really sloppy, but do you see what I mean? So those are the zones of increasing and decreasing. So we're increasing on the right-hand side of the green line when x is bigger than 1, because this is green lines when x is equal to 1. So we're increasing when x is bigger than 1. We're decreasing on the left-hand side of the green line where x is less than 1. Okay. And then finally, is it a function? Why, yes, it is. It does not double back over itself. All of the outputs are unique to the input. We're good. All of our opening upwards and downwards parabolas will be functions. Okay, so I'm going to give you a few seconds to try to finish writing those things down, and then we're going to move forward. All right, here we go. So for this one, I'm just going to sort of jam through this much faster, okay? So right away, I can see, excuse me, change my color. Right away, I can see that this is a parabola. It's a quadratic. I can also visually see it in the graph because the graph is done for us. So I'm going to go ahead and type that in. The shape is parabola. All right, that's good. Okay, this parabola now opens down. So if you put arrows on the ends, like you can draw in arrows. I'm just gonna, I have a little arrow tool, so I'm gonna use my arrows for my arrow tool. So this opens down. That means it has a highest point, the top of the mountain. So that tells me it has a max or maximum. And the maximum is at the vertex. And be careful, your vertex is actually, if this is 0, 0 right here, 1, 2, 3, 4. It's actually at 0, 4, not at 5, which is, it sort of looks like it's at 5, but it's at 4. So our vertex is at 0, 4. That means our line of symmetry, which is this line right here, which is actually our, oh my goodness, it's actually our y-axis this time, our line of symmetry. The equation for the line of symmetry is still going to connect with the vertex. It's going to be the x of the vertex, x equals 0. That's the equation of the y-axis. All right, looks like we have two x-intercepts here and here at -2, 0 and 2, 0. Looks like we have a y-intercept up here at 0, 4, which is also our vertex. All right, based on that, oh, we know the domain is always all real numbers. We know the range is going to be everything below the highest point, and the highest point is 4 in the vertical in y. So we're going to say that the range is all the y's less than or equal to 4. And I'm going to go ahead and put my equal to part of my symbol on there, less than or equal to 4. And then I'm increasing, let me change my color so you can see it. So I'm increasing on the left-hand side of this. This is all increasing, and then decreasing on the right-hand side. Do you see that? So increasing on the left before x is 0. So this is when x is less than 0. I'm increasing, and decreasing after when x is bigger than 0. And these are all functions. So the last thing to do is to fill in the table. And we want to make sure that we organize it really nicely. So I'm going to go ahead and put the vertex right in the middle, 0, 4. And then I need a few other points. So I'm going to go ahead and get my drawing tool here and find a few other points. So we've got the x-intercepts. Those are 2 good points to use. We also could use, like, what about this one and this one? We're looking for like a spot right on the grid line where it's whole numbers. So that looks like -1, 3 and +1, 3. So those are usable. We could also use these over here, 3, 3, -5 and -3, -5. Either of those would be fine. All right, so I'm going to go ahead and use these littler ones. So I've got -1, 3 on the left-hand side of the vertex. and 1, 3 on the right-hand side. And then I'm going to put in my x-intercepts at -2, 0. And 2, 0. And just to make sure that we're really clear on this, all of these XY pairs could be found by plugging X values into the original equation. So if you substitute a 0 in for X, you see how 0 plus 4 is 4? You're going to get out the 4. If you substitute a 1 in for X, 1 squared is 1, it becomes negative, add 4, and you get 3. Do you see? Like you're going to get the outputs for those inputs using the equation. It connects with the equation as well. Okay. All right, any questions I can answer about those? Okay, for this next one, I'm going to start it with you, but then when we get to the description parts, I'm going to have you do independent. Okay, I'm going to just have you try to do it on your own. All right, so like I said on the previous one, how the inputs and the outputs can come from the equation, I'm going to do that here. Do you see how we have all these inputs, 0, 1, 2, 3, and 4, but nothing else? But we do have the equation. So what I'm going to do is start substituting these values in for X here and here to get the Y that goes with it. So when you put a 0 for X here and here, you actually get a 5 out. If you put in a 1, 1 squared is 1 minus 6 times 1 plus 5. That gives you a -5 plus 5, which is 0. Plug in a 2, you're going to get 4. 2 squared is 4 minus 12 plus 5 would give us -3. Plug in a 3. That's 9 minus 18 plus 5 is, I think that's a -4. And then when you plug in a 4, 16 minus 24 plus 5 is -8 plus 5, which is -3. So this table isn't actually balanced like our previous ones in the same way. But I do see a little hint of symmetry here. I see that we have -3 and -3. Do you see that? Like -3 and -3. So this makes me think that this is probably my vertex. This is probably my vertex. Let's graph them and see what happens. So I'm going to go ahead and plot my points. Okay, so 0, 5. Oh, I was trying to make my pen bigger so that I could make like a nice big dot. Okay, 0, 5. 1, 0. Yeah, that's sloppy. All right, let me do this with the highlighter. Okay, 0, 5, 1, 0. 2, -3. 3, -4. 3, -4. Mm, 4, -3. Okay. All right. So let me pause for a second here. All right, so those are our points. And if I get my line tool or my drawing tool and I connect the points, I want to try to make a nice smooth curve. So it should look something like this. Kind of good enough-ish. And just to be clear, we're at 0, 5 here. We're at 1, 0 here. We're at this point here, this point down here, this point here. And we have symmetry. So there should be a line of symmetry right through this point. So if we're thoughtful about this, then we should probably assume there's another point right here, exactly 2 units away from that line, that green line on the other side. And another one right here as well. Like we have those symmetrical points. So even though they're not in the table, they are a part of our curve. Okay. All right, so now that we have our curve, we can start typing in all of our stuff. So what I'm going to have you do now is try to describe the graph with all these details based on this visual. And I'm going to put it on student paste so that you can go back to any of your previous slides if you need to. Okay. And then let me know if you have any questions, like jam through this. And if you feel confident and you want to go on to the next ones, go ahead and do it. And if you feel like you have any points of confusion, please don't hesitate to put it in the chat and I will try to clarify. Okay. So I'm going to give you a few minutes to work on this and then we will go through it together. Okay. So going through the answers. So the shape, again, it's always parabola for these. This one opens up. It has a minimum at its vertex, which is at 3, -4. There's a line of symmetry that goes right through the vertex at x equals 3. That number will always match the x in the vertex. Okay. The x-intercepts here are at 1, 0, and 5, 0. The y-intercept is over here at 0, 5.
This meeting's being recorded, right?
Yes.
So I can just come back to it if I need like a reference point for this kind of stuff.
Yes.
Okay.
And now you will be on the recording. Okay. And the domain is all real numbers. And the range is everything from that lowest point and up. So our cutoff is at -4. So we would have all y's greater than or equal to -4. So I'm going to add that little equal to my greater than or equal to. There it is. And then our graph is, let's see where it's increasing and decreasing. So on the left-hand side, it's going downhill from left to right. So that's a decreasing zone. And on the right-hand side, it's going uphill. That's an increasing zone. So we're decreasing on the left-hand side of the axis of symmetry, which is x equals 3. So we're decreasing when x is less than 3. But we're increasing on the right-hand side of the axis of symmetry when x is bigger than 3. So x is bigger than 3 is our increasing zone. And all of these will be functions. So that's a yes. All right. Here's number 4. All right, number 4. Okay, so in number 4, this one sort of behaves similarly to other ones. We have the graph all ready for us with our equation. You can see how it is a quadratic based on that exponent there. And so I'm going to start typing in my details. So this one's a parabola. And it opens down. And so this stuff hopefully is feeling like pretty straightforward now. So I'm going to give you a few minutes to try to do some on your own and then let me know if you have questions and then we'll go through it together. So once again, we know it has a maximum because it looks like a hill and there's a highest point. So that is considered the maximum. So our maximum in this case is it's a maximum and the maximum is at the vertex 1, 0. The line of symmetry that goes right down the middle, it always goes through the vertex, and that line of symmetry has an equation of x equals 1. And this number will always match this number. So the 1 for the axis of symmetry is the same as the 1 in the vertex. They will be matching. X-intercepts are where we cross the x-axis, and you can see it only happens once at the vertex this time. And the y-intercept is where it crosses the y-axis, and this one's at 0, -1. And then the domain of our parabolas, of all of our parabolas, are going to be all real numbers. Whoa, sorry for the shouting. Okay. I'll pause for a moment. All right, so now we have all real numbers. All right, our range. Our range is what y values can be used, so our outputs. And in this case, excuse me, we have a max. And because we have a max, that means that all of our numbers for y will be below a certain like cutoff at the top. And the highest number we reach in terms of y is actually 0. Do you see how in the vertex 0 is our y of our vertex? That determines for us our range. So our y will be less than or equal to 0 in this situation. And I'm going to go ahead and I'm going to put my or equal to on there so that we're really clear. It can be equal to 0, but it can't be above 0. Oh my gosh, I can't even write that. There you go. Okay, so y is less than or equal to 0. And then where we're increasing. Okay, so I'm gonna get my little arrow tool. So we are going to be on the left-hand side. We're gonna read from left to right. So we start over on the left and we follow along the graph, and it looks like up, up, up. That's the increasing section of the graph. So when I go over to my list, I'm increasing on the whole side of the graph where x is where we're to the left of the axis of symmetry. That means where x is less than 1, we're increasing. Now I'm going to change my color. After the vertex, we're then going down, 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 downhill. So this is decreasing on the right. So this tells me that we're decreasing where x is bigger than 1, because that's to the right of 1. And then is this a function? Why, yes, it is. Okay. And I do have a table to fill in. So I'm going to put my vertex in the middle. I need 2 other points. So I have, let's see, the y-intercept is at 0, -1. So let's put that one on the left. And I need a balanced point on the right. So it looks like 2, -1 on the right would be balanced with that other point. And then let's go further. It looks like we have one down here at -1, -4. And on the right, a symmetrical point from that is at 3, -4. And you can see how in the table we have this symmetry, -1 and -1, -4 and -4 on either side. Okay. All right. And I do have to hurry up and do the last one due to that I have tutorial. Okay. So here, this one's actually giving us weird information. It's a little different. So you can see how we have a vertex at 2, 9 that's given to us. I'm going to go ahead and graph that at 2, 9. There's our vertex. And we have x-intercepts at -1, 0. At least that's one of them. And a y-intercept at 0, 5. And we have to find everything else from that. Well, if that's our vertex up here, then this means that our graph has a line of symmetry that goes through that. So I'm going to go ahead and put that line of symmetry in. This is our line of symmetry. So what I'm going to do is find a few more points based on that line. They have to match on the other side with the points we already know. So we've got our vertex. this point is 2 to the left of the line, so I'm going to have another point 2 to the right of the line. And this is 3 to the left of the line, so I'm going to have another point 3 to the right of the line. So there is my parabola. So that's kind of sloppy, but hopefully you get the idea. And this means that we have another y or x-intercept. This is our x-axis and our y-axis. We have another x-intercept at 5, 0. So there we can fill that in. And then now I'm going to start filling in my table. So I know I have 2, 9 as my vertex. I have 0, 5. And then this one is 4, 5. And then I have -1, 0, and 5, 0. So there's a table. And I'm going to type in all my answers here. So parabola opens down. It has a max at that vertex. X equals 2. I'm just copying the number from the vertex in the X. The domain, all real numbers, always. The range, I'm keeping my y's below the 9 in our vertex because it's got a max, so everything's below that. So y is less than 9. Go ahead and add this little notation here, less than or equal to 9. We are increasing on the left-hand side of our axis of symmetry. So we are increasing when when x is less than 2 on this side. And we are decreasing when x is greater than 2 on the right-hand side. And is it a function? Yes. And there we have it.